Okay, so it's time to get started. So good morning. Um, there's a couple of announcements for today. Uh, First, your second exam for the modeling component of this class is going to be this week on Thursday. So make sure that you prepare for your exam. The exam is going to be following the same format as the first exam. So you're going to have an exercise that is going to be based on the labs that we cover after the first exam. So you just have to make sure that you understand those exercises and that you know how to build those models by yourself. You're going to have an hour and a half for working on that exam. So based on the experience that I had on the first one, some of you were able to build a model, but there were certain details that were basically pushing you to stay longer. So again, my recommendation is just make sure that you understand how to set up a schedule for the arrivals, for the capacities, how to name those, how to put them when they belong. Make sure that you know the difference between an attribute and a variant and a variable. Make sure that you know how to set up your statistics. And if you're comfortable defining those, you should be able to do very well on the exam. Now, in terms of the course, the theoretical component of the class, today is going to be our last lecture in that sense. So we're going to complete this topic and we're going to discuss an additional topic today. But on Tuesday, I decided not to give a lecture because I want you to focus on finishing the project. Okay, so I want you to take that time to make sure that you set up your simulation model, you get the results that you need, you put it together your project report and also your presentation. I haven't put a template for the project report or the presentation, but I'll do that today. So you have enough time to plan for what you need to do. But make sure that you go and work on those things because that's going to be the last part of or the last lecture of this semester. It's going to be your presentation of your findings and your project. You're going to have about the same time, 12 minutes to present. So most likely you're going to be presenting your problem one more time, the model, maybe if you can run your simulation to show us your model, and then present the results and your recommendations. That's basically it. So that's, and the last thing is you will be having your final on the scheduled date. So that date is on the syllabus, and that final will basically cover the topics that we started lecture 5, 6, and 7 that we're gonna go over today. Any questions? Okay, so let's get to work. So today we're going to continue talking about manufacturing systems, but in the sense of production scheduling. So we already started discussing some of these topics. We talk about different algorithms, that this is an area that has received a lot of attention from the community in industrial engineering. So there's different algorithms for different case of manufacturing processes and parallel machine scheduling in particular. So we're focusing on some of those aspects. Um, we talk about the goals of production scheduling. We talk about how the computational time will increase when you start adding more jobs and more machines into your problem, and your solution time will be getting very, very high as you start adding more details into your problem. So there are certain things that we can do. We can add more computational power to finding those solutions, or we can devise some new algorithms to work with those problems. Okay, so we talked about some of these things already. Today we're going to focus on the last few points: bottleneck scheduling, diagnostic scheduling, and production scheduling in a full environment. So starting with linking planning, and scheduling, we have another option to for variability reduction, post production, and efficient batch sizing. Methods all make a production system easier to schedule, but there's another technique that we can use for simplifying scheduling, and that is known as due date quoting. Okay, so there's certain scheduling problems in which you're gonna have due dates for all the parts that you're gonna be scheduling. So these type of problems, scheduling problems involving due dates, are extremely hard to solve because in addition to having to schedule the parts into a machine and considering the lead time and so on, you also have to take into account that when the part has to be delivered. And that can be the same for all the parts, and it can be different for each one of the parts. So due date setting problems can be relatively easy. This strategy will seem worthwhile. So the difference between having the due dates set and counterpart to that is we're gonna set up these due dates in our convenience. Okay? So scheduling problems involving due dates are hard, but if we have the flexibility of setting up those due dates ourselves or based on our system performance and our system capacities, then it will make things easier for us. So here's an example of some of the things that we need to consider when we are looking at production, when you have to set up your due dates. So you have a new job that you need to schedule right here, and you already have some work that are being waiting to be processed, some of them already in the factory, and then you have a rate of output, some of the things that are already completed. So you have several things that you can do in order to accelerate the time that this new job will require to be completed. Obviously, if you put it in the first in, first out strategy, you're gonna have to wait for all these parts that are already in line and the working process to be completed for you to be able to process that part. But there are other things that you can do. For example, there's a strategy in which you can leave some emergency positions, and that means that you can put that job up front because you are planning for having those cases already in your production schedule. And if that's the case, then for example, you can put that job here. That would put you on a better perspective in terms of satisfying a due date, for instance. So you're gonna have a rate. We can also model that rate of completion using a probability distribution with a mu and a standard deviation. But in terms of if you put it into a FIFO strategy, you know that it's going to take you this many positions to be able to complete that job. So I'm representing here with W plus B plus C. That means that you have to wait for all the working process, the backlog, and then the position in which you are at that point. So an analytical approach for a dynamic due date quoting is presented in this slide. We're going to use some notation. And again, there's some probability models here involved. So there's always a chance for getting that process completed on time. So for example, XT is the work completed during period time T. Mu is the mean work rate in standard units per period or per time period. You have the standard deviation of the work rate. M is the work ahead of and including the current job. So this is how many units we have in front of us, including the unit that you want to process or you're considering at that point. We also have a desired service level, so that's the quality of service that we can achieve or that we would like to achieve for the customer. And then we have L, which is the minimum due date to attain the service for a current job. Okay, so the desired service level, this is going to be expressed as a percentage or a decimal point. So we want to make sure that the probability that we satisfy this number of units to be completed, when we know that the position is less than or equal to this number, it is equal to that level of service. Okay, so the probability of not completing n units of work within that lead time is given by this expression. Now, we can compute the due date quote using this expression right here. If you're familiar with the normal distribution and the standard normal distribution, that C is what that is representing in terms of a probability. So we might need to use the probabilities coming from the standard deviation, from the standard probability distribution from the normal distribution to compute this due date quote. Okay, so L is going to be the minimum due date to be able to satisfy that current job service level. So, for example, what we're trying to say here is, okay, I need to process this job. My customer, I want to keep that customer happy in the sense of satisfying the level of quality of service that he wants to have. So this is the earliest that I can, this is the date or the earliest day that I can complete that job so I can keep that level of customer satisfaction. Okay, so that's what this expression is giving us. Or, so we have a safety lead time here. So this is basically what is covering the date or pushing the date to a certain level so we can satisfy that customer level. So what happens if the standard deviation and is equal to 0? So we come back here. If the standard deviation is 0, no variability is involved, this whole term will go to 0 because this is going to be 0 and the multiplication will cancel or will make that whole term equal to 0. So if there's no variability, we know that that lead time or that due date that we are going to quote is going to be equal to the number of positions divided by the standard or the average rate of production, regardless of S. So that means quoting M divided by mu days will achieve a 100% service in a system with no variability. And again, that makes sense, right? Because you're taking out all the variability, so you're going to be quoting this L, and you know that that's the lead time that you're going to need to be able to satisfy that customer. So there's no variability involved. So the due date is increasing in the sense of the standard deviation. So more variability will require more safety lead time. So what this is saying, okay, if I have a lot of variability in my process, then I need to give an extra couple of days for me to be sure that I'm going to be delivering the product on the due date that I'm promising, and I'm satisfying the customer level or quality of care, of level, or the level of quality for the customer. So in order to achieve its service of at least S, we must round up to the next integer to arrive at the due date to quote in units of full days. Okay, so if your answer is in terms of a decimal number, 9.3, for example, you're going to round up because you want to make sure that you are covering that extra 0.3 days as part of your safety lead time. So next, I'm going to be working on an example for this type of problem. So here's the data. S equals 0.9. So again, we go back here. So S is the desired level, service level. So we are targeting a 90% level, service level. Z of that service level is going to be 1.28, and this number again is coming from the standard normal table. We have, and for the purpose of this class, I'm not going to be asking you to look for this number. If I ask you for a problem like this, I'm going to be providing you the actual number from the table. But you should be familiar with these concepts at this point. So at least have an understanding of what the normal distribution is, how does it look. So it's a bell-shaped distribution, and we can standardize that probability distribution so we can get a probability from 0 to 1 or a normal 0, 1, which means that the normal follows mean equal to 0 and the standard deviation equals to 1. And using those numbers, we can standardize the probabilities. So that number is coming from the standard normal. We have a mu of 100 pieces per day, standard deviation of 30 pieces per day. W, again, is coming from the width. So this, we have 500 pieces in line. We have 900 pieces on the backlog, and then Z equals 100 pieces in the current chart. So that means that we need to satisfy this number of units for the customer. And we already have this many units in the system. So if we compute the number of pieces that we need to complete in order to get to this customer, that's going to be 1,500 pieces. Okay, so we can compute the lead time following this formula right here. So we want to know how many days we should quote, or let the customer know how many days we need to in order to satisfy that order with that certain level of service, which is 90%. So we are just substituting these values into this equation, and the answer again is in terms of decimal number. So that's why we are rounding up to 17 days. Anything, it doesn't matter if this is 0.5 or 0.1, you always round up because you want to make sure that you are covering that extra portion of the day that you're going to need to quote the customer. So the interpretation here so if you look at this part right here, you know this is 15 days, right? So in a system with no variability, that's what you're going to be quoting. But of course, we have some variability in our system. So what this is computing right here is 2 extra days for the safety lead time, just to account for that variability in the process and make sure that we can deliver the pieces on time. So note that n divided by m equals this, which is equal to 15 days. So to accommodate the variability, we are building in 2 days of safety lead time into our quote. Okay? So another way that we can look at these problems is, so we were talking about the dynamic due date quoting. Another way to look at these scheduling problems is scheduling via log sizing. So determining the best size for your lot. And here we have a case study for TJ International. We have a parallel product. So we follow this process. We have 3 operations in order to get to the final output. So the issues here means, here we have in our bottleneck. So this is a bottleneck of the process. And we have different products, so there's a 12-hour changeover time to switch between the 12 inches, 14 inches, 16 inches, and 19 inches products. Many products made from each width, but less 14 inches and 16 inches than 16 inches and 19 inches. Currently try to run at least a week between changeovers. So you want to run these processes without having to change between width for at least 1 week. And seasonal demand. So we have a seasonal demand. That means that the product will go faster certain times of the year than others. So we build an inventory up in the off-season. So what is the problem? We need to determine the run sequence for each month. Okay, so here's some notation. So we have the capacity, hours available, and this is in terms of days per month times hours a day. So we're basically going to have this estimated in terms of hours. We have a desired utilization for the system. We have the monthly demand, so parts per month per product I. We have the hourly demands, parts per hour for product I, the production rate for each one of the products, the setup time in terms of hours for each one of the products, and XI is going to be the lot size for each product. And this is what we want to answer. So we want to know what the lot size could be or should be, so we can make sure that we don't put that as many chain overs in our system. Again, it's taking 12 hours for each chain over to be completed. So if we can get as many units of one type in a row and then do the chain over, we can increase our throughput. So the problem is choose lot sizes for the month to meet demand as efficiently as possible. Okay, so you're not familiar with optimization models, but in optimization models, well, some of you are, some of you probably not, but you're going to be familiar with those next semester for sure. So Dr. Noah is going to be teaching you some of those concepts in one of your classes. But the idea in optimization models is that you're going to have linear programming models, integer programming models. You're going to have an objective function. That objective function is going to lead your solution. Basically, if you want to maximize your profit, your decisions are going to be made according to that objective function. If you want to increase your throughput, then your decisions are going to be made based on that condition. So that's the type of model that we're going to need to solve this problem. Also, in those type of models, you're going to have always a question to be answered. So, so in this case, we want to know the lot size. We want to know what is the best lot size so we can improve this performance measure. Okay, so so there's multiple things that we take into consideration here. In this case, we have cyclic schedule. So the approach is to fix lot sizes for all products and compute the number of cycles that can be run in the month for that specific product. Okay, so we're going to fix the lot sizes for all products, and then knowing that lot size, we're going to have to estimate how many of those we need to run, or cycles we need to run in order to achieve our goal. So we can compute that, the number of cycles that can be run in the month, as this. So n is going to be equal to u times h. We have that notation here. So U is the desired utilization, H is the hours available. Minus the summation of DI divided by PI. So DI is the monthly demand, PI is the production rate. Divided, all of that divided by the summation of SI. And SI is the setup time for each product. Okay, so if the horizon is short, or the time horizon, that's what we are referring to here. If the horizon is short, n should be rounded down to the nearest integer. Otherwise, a non-integer n is okay, and you will be rescheduling anyway. So if we don't have enough time, basically what we're saying is, and this is kind of subjective, I would say round down anyways. You will round down and you're going to keep the number of cycles small. You're going to round down to the nearest integer, so you can add more capacity in terms of the number of products that you can add to your system. A non-integer otherwise is okay since you're going to be rescheduling anyways, meaning that you're not going to have enough capacity, so you might need to go for extra capacity at some point. So in terms of the lot sizes will be equal to xi. So you're going to have the number of cycles, and then you're going to have the actual demand for that product, and that's going to give you the number of cycles for that, or the lot size, sorry, for that particular product. But for that, you need to compute, obviously, the number of cycles that you're going to be able to do. And again, here for the total number of cycles, is it just for one product or you're considering all the products? That's a question for you. So if you look at the expression, you're doing a summation here for all i's. Okay? So that's considering all the products. So when you compute n, you're basically saying this is the total number of cycles that I have, or that I can get into my system. Now I want to know for each product how many, the lot size for each product based on that. Okay, so I know the number of cycles that I can put into the system. I know the demand for each one of the products. So based on that, I'm going to decide what is the lot size for each one of the products. Okay, so here is values must be rounded up. Okay, so the problem, sometimes you don't necessarily want to make the same number of rounds for a low demand product as of a high demand product. So that's a fundamental issue with the non-cycle schedules. So the fundamental issue here, what will be your objective? Or what is your objective? Maybe minimize the sum of the run length. If we write out the Lagrangian for the nonlinear optimization problem and optimize assuming continuous lot sizes, we get these expressions for the lot size for each product. I know there's a lot of things here that you are not familiar with, Nonlinear optimization is there's linear and nonlinear. Linear optimization means that your functions, or the functions that you're going to optimize, follow a linear function. So it's line, right? Nonlinear optimization is the opposite. Instead of having a linear function, you're going to have a nonlinear function such as x squared. Okay? So there are certain strategies for solving those type of problems. One of them is called the Lagrangian. We basically, these problems that are nonlinear usually are very difficult to solve. So this is one of the strategies for solving those type of problems. The idea here is that for non-cyclic schedules, we can come up with this expression based on those strategies. We don't need to go in deep understanding how we achieve these expressions, but we have these formulas. Okay, for non-cyclic schedules. Problems are, since we solve for lot sizes, we went up with a non-integer number of setups for the month. So how do we allocate the setup time? Another problem is what order do we run the products in a non-cycle schedule? So again, these are questions that not necessarily have a specific answer. So in conclusion, we should solve for the number of run cycles for each product we should solve for the number of run cycles for each product. But again, what will be the objective? What is that target that is going to give us our solution? So, but what objective do we use? Okay, so next I'm going to show you a particular objective that we can follow. So this is called minimize the maximum run length. So for all the products, we know that this is a non-cyclic schedules. So for all the products, basically we want to minimize. We look at the maximum run length for each one of them, and we want to make that one the minimum possible, or the shortest possible. Okay, so we keep most of them within the same length. So following this objective, we are never too far away from changing over to another product, and also provide some flexibility. There's some notation again here. We let Ni, the number of times the product I is run, in H, and that's going to be our decision variable. And then Si plus Di divided by Ni times Pi is the run length each time product I is produced. So H, did we define H here? Yes, so H is the hours available. Okay, so the number of times product I is run in these many hours that we have available. And then we have the run length each time the product is produced, which is going to be based on that number in I. And we can formulate this as a IP formulation. So again, this is going back to the optimization course that you're going to be taking next semester. But the idea here, we have a decision variable which is again the number of times that we gotta run this product, and we want to find that answer to that question by minimizing the t, which is gonna be the total time available. Okay, so we want to be able to do all these things in the minimum time possible. So, as an example, let's look at this problem. So we have 4 products. We have the demand for each one of the products here at the top. PI, let's go back here to the notation, is the production rate, parts an hour. So this is the number of parts that we can produce an hour for each one of those products. SI, again, go back here, is the setup time for each one of the products, and that one is in hours. Let me keep track of this. So everything is set up in terms of hours. So this is set up in hours, and this is parts in hour, and this is the demand. And if we look at DI divided by PI, it's just this divided by this, and this is the value for that expression. So suppose the plant has a policy of never making less than 1,500 units, so their current lot size are 1,500, 1,200, 1,500, actually this is 15,000. Actually, 15,000 comes from here. So suppose the plant has a policy of never making less than these many units. So the current lot sizes are the following. Okay, so we are making more than 1,500 every time for each one of the products. This takes 19.2 days, close to the 22 days available. But it means that some products won't be produced until pretty late in the month. So we can compute the number of cycles per month. So the number of cycles per month is equal to n, and n is going to be equal to, back here, this expression here. Okay, so n equals 396 times 0.9 minus 281.67 divided by 26. And this is equal to 2.87. Yielding lot sizes of. So if we go and find the expression for lot sizes, it's right here, it's xi divided by di divided by n. So that will give us the following. So xi equals di divided by n. That will be equal to, let me make this a table. So I equals 1, 2, 3, 4. So I have xi here. This is 5,219, 4,175, 174, and 87. So that basically means that you're gonna run 2 cycles of product 1 using this many units, and then a third cycle that will be 80%, 87% of this number. You don't need to follow for round 3 complete cycles because you are only needing 2.87, right? But n equals 2.87 means that the first 2 cycles in the month use the above lot sizes, while the last one uses reduced lot sizes 87% of base. We can also look at the minimax schedule. We can implement the formulation as follows. So basically, this is the greedy approach. We start with Ni equals 1 for all i's, and know that the product with max run length is product 1 with a run of 158 hours. So you can add setup for product 1. So N1 equals 2. The max run length becomes 83. And now product 2 has the longest run length at 128 hours. And then we have set up for product number 2, so N2 equals 2, and its max run length becomes 68, and now product 1 has the longest run length at 83 hours. And we basically continue this video approach, adding setups to product with the longest run until we run out of capacity. So if you continue this process, you're going to end up with the optimal solution of having Ni equals 4, 4, and 1, 1, and with the lot sizes of 3750 for 1, 3000 for 2, 500 for 3, and 250 for number 4. So again, a greedy approach type of algorithm to get to the solution of the minimax schedule. In terms of the results, the schedules goes as follows. One, we set up for the fourth product, and because it's the one that is requiring less, 250. So we set up for that product and we get it out of the way, and likewise for the third product. And then number 3, now we run $3,750 of product 1 and 3,000 of product 2 in succession for 4 times. Okay, so you see, this basically say that you only have a run for these two, so you start with those two, you take them out, and then for these two you have 4 cycles for each one of them, so you're basically are going to be switching between them for 4 times. The longest anyone will ever have to wait will be for product 2 at the beginning of the month at 3.73 days. After that, the longest wait will be 2.53 days. So as a conclusion, the minimax schedule results in shorter wait for product than either minimal run schedule or cyclic schedule. And also it is simple compute. Okay, so From here we can transition to bottleneck scheduling. I think this is the last topic of this lecture. So this goes back to scheduling in full environment. So simple conduit lines, there's a simple sequence to be sufficient with no setups. But when you have a conduit line with shared resources, no setups, you need to augment the sequence at shared lines in first in, first out in terms of the assignment at the shared resources. So here's an example in which you have routing of A and routing of B. So you start with processing those parts. Again, you are going through a full environment, so you're going from the back to the front, requesting units from this portion of the process, and then going back here as following that FIFO sequencing. Conduit lines with setups, sequence still reasonable. You must balance capacity loss with the due date requirements. There's no possible exact solution. So that means that there's no easy way to find the optimal solution. It's almost impossible. But heuristics starting with earliest due date and rearranging sequence can work well. So heuristics are algorithms that not necessarily are going to give you the best solution, but are going to give you very good ones. And what this is saying is, if we can use some heuristics, basically search procedures for allocating these parts in the machines and finding if we move this one to this place, what is the improvement? If it's a good improvement, we'll keep it in that position. It can work well in this type of environment. More general environments, many routings make simple sequence insufficient. Backward scheduling, due dates may be infeasible. Forward scheduling, again, may be suboptimal. So no optimal solution. So the best we can do here is to find good solutions for our problems. So a sequencing example here, we have a problem with 16 jobs. Each job takes 1 hour on a single machine, which is the bottleneck resource. We have 4 hours set up to change families of parts. We have fixed due dates, and we want to find feasible solution if possible. So here's the information that we have for the products. So we have 16 products. Each one of them part of a specific family. So we have 3 product families. We have the specific due dates for each one of these products, and right now they are sorted based on the due date. We also have a completion time right here for each one of the products. So it's going to take 5 units for this one, 6 units for the completion time is actually the time it's going to be taking to complete the part after processing the previous one. So from here I can get, so the due date is 6. The completion time is going to be 6, so that means that there's a 1 unit completion time for part number 2. But what the table is showing here is if you sort them based on the due date and you compare that with the completion time, this is giving you the lateness for each one of those parts. Okay, so for example here, this part is due on the 10th, but you can complete it by the 7th, so you have 3 extra unit times for processing another part. So for the next one, the completion time is 12, the due date is 13, so you're finishing that part earlier, but then you start seeing the problems. After this unit right here, you start being late. So this one due date is 15, but you're finishing by the 17th, 15, you're finishing by the 22nd, 22nd, you're finishing by the 27th, and so on. So after this point, you're starting to be late to complete those parts. And the average tardiness for this problem, or the average number of units of being late, is 10.375. Okay, so that's a problem. So how do we solve this? Can we do better for this type of problem? Can we do better than just putting them in by due date or sorting them by due date? If you look at this, there might be some improvement strategies for these specific problems. So, for example, there's certain parts here like this one, in which the due date is the 29th, and it's currently late because it has to wait for the other parts to be completed. But maybe if we push this one to be earlier in the process, then you can add an extra part that can be completed in time. So that's the idea. How do you sort this in such a way that you can minimize this tardiness? Okay, so there's some greedy approach here. You can consider all pairwise interchanges. So you're basically trying each position for each part. So you have 16 jobs, so you're putting each job in each position, and you're finding what is the best position for each one of those jobs. Choose one that reduces the average tardiness by maximum amount, and continue until no further improvement is possible. So the first interchange, as I was saying, is to change job 4 and 5. So you're making this switch right here, and you are adding an extra job here that can be completed in time. So that average tardiness reduced by 5.375. Okay, just by making that switch. Because the other jobs can be also improved based on that. Configuration after the greedy approach. So this is after looking at all the possible interchanges that you can do. You see that the average tardiness was reduced to 0.5 after looking at all the possible changes in the system. So very difficult to do by hand. Obviously, you wouldn't want to do that by hand, but these type of problems can be easily implemented by a for loop logic in any Java environment or C++ environment, and by running it into the computer, you can find these solutions easily. A better feasible sequence here, actually, you're able to get the tardiness to 0. So here you're seeing jobs being processed like 7 towards the end of the sequence, and so on. So again, after performing this extensive search, you can end up having very good solutions. So that's just a point that I wanted to bring to your consideration. They are not necessarily very high analytical procedures, but they're very powerful. Right? Very simple search like those can give you very good solutions. Now, in terms of diagnostic scheduling, the goals are to schedule an appropriate level of detail for an environment, make use of realistic, obtainable data, and accommodate intangibles in the decision support mode. So the approach is having a deterministic model based on conveyor model, and you try to release as late as possible, subject to due dates, and then provide diagnosis on the infeasibility. Types of infeasibility include WIP. So this is cost by inappropriate positioning of web, and then capacity, this is caused by having insufficient capacity. So you don't have enough machines, so you don't have enough operators. So these are the two types of infeasibility that we are looking at. Are you putting enough web, or you're putting too much web into a particular station of your process? Or are you planning for enough capacity for you to be able to run this process? So for example, here we have a capacity of 100 units per day. The minimal practical lead time is 3 days, and the WIP in the system with 1, 2, 3 days to go is 95, 90, and 150. So on day 1, we have 95, day 2, we have 90, and day 3, we have 150. Okay, so consider this type of line. So if we have a capacity of 100 items per day and a minimal practical lead time of 3 days, we can compute at full capacity. Total WIP that we can have is 100 times 3 days, which is 300. So on the next slide, we have some infeasibilities that we can observe. So for example, we have the days from start, so from 1 to 15, the amount due. So we don't have that. So this is the amount due per day. So on the first day we need 90, on the second one 100, on the third one 90. And the cumulative amount due is basically the sum of these columns. So we have 90, 190, which is 100 times 90. 90 times 2 plus 100 is 280, and so on. So if we look at this number, the weapon system for 1, 2, 3 days to go, for the first day we have a community capacity of 95, right? So that's enough to satisfy that demand. So we have 5 extra units here that are, so we have 5 extra units. And then on the next day, we have how many? 90, right? So that means that we have 185 available, but the amount due is 190. So we are getting short by 5 units. So that means that the WIP that we have in the system is not enough to satisfy that demand. So there's a WIP infeasibility at this point. And then if we continue, we don't have the information for for all the products, but at a certain point, you'll see that you are not going to be able to reach out to the demand. And that will happen after this point right here. So at that point, you can understand that even at full speed or full power of your system, you're not going to be able to target or to achieve that target. So that can illustrate the inherent feasibility in terms of capacity. So you might need to add more capacity in order to achieve those numbers. Okay, very simple examples, but they're illustrating several things. So here's the plot of the same thing. So cumulative demand versus cumulative capacity. So the amount due is in blue, and the amount and the current capacity is in red. So you see at some point your capacity is below that specific number. So that's it when we start seeing the problem at 8 right here up to 14. Okay, and then at some point we start looking at making enough, probably because the demand of the system went down. So when the demand went down, then we cannot got to speed with the system, and that's what is illustrated here at the end of the graph. Now, in terms of surplus, so we see that the width that we had available at the beginning was not enough, so that's why we have this point right here. So that's showing that width in feasibility, but after this point, we were able to cover the demand, but then we spend more time under the curve for how many time units, or 1, 2, 3, 4, 5 time units. So at that point, we can say, well, for 5 units of time, we are not able to satisfy the demand, so there might be some capacity and feasibility in the system. So in summary, we can say some things about scheduling. Scheduling is hard. We saw that there's some certain things that make these problems difficult to solve. Every simple toy problems generate complicated mathematics. Scheduling can be simplified through the environment. So if we can quote the due date, for example, or by simplification of the flow, sequencing in place of scheduling. Finite capacity scheduling is coming. This was the next topic that I wanted to cover, but we will not have time. But you will see those things, these topics in the class. There's a lot of operational research in that topic. So I was basically planning to touch on some of the things, but I think it will make more sense when you start taking operational research next semester. And diagnostics are important in scheduling. Here, continuous optimization generally is impossible to achieve with this problem, so algorithms are needed. And need good interface to allow human interactions. And I can testify about that. Scheduling, for example, in hospitals, not worth it if the person that is familiar with the system cannot interact with the scheduling platform. Okay, so any questions? So again, I'm going to stop here. Topics that are going to be included in the exam, then it's just going to be based on lecture 5 and 6. We have 2 parts for each. Sorry. We have 2 parts for each one of those lectures. So the exam should be kind of simple. Hopefully you'll do very well. Make sure that you put some time into the project, giving you that lecture just because I want you to do well. I was thinking that for those of you who do a very good project report, maybe we can consider looking at a conference to submit a paper, and maybe you can travel and present that project report. So think about that too when you're writing your report. So, any questions? Yes. Yes, so I'm gonna post the homework today for this chapter, and that will be due on Tuesday. Um, Again, we can meet, we can come collect the homework that day and be here to answer any questions about the project or the exam. Um, but we are not gonna have a formal lecture. I want you to spend time on the project. Any other questions? So I think we need to leave the room for the next class. I brought your homework, so you can pick up your homework here. And the solution is going to be posted today. I'm also going to post the solution for the lab for you to use that as preparation for the exam. So you still need to submit your lab, even though I'm going to be posting the solution. So that's going to be available today.